So now we're ready to state the first version of our Fourier inversion theorem. So the idea is that if you have a function inside B1 of G, that's essentially everything inside B of G and also inside L1, then automatically, first of all, your Fourier transform, the f hat, is going to be inside the L1 of your G hat. Okay, so that's a L1 function on the dual group. And moreover, all these f hat is going to be enough to recover your function. So what do I mean by that is that you can normalize your Haar measure on the G hat. The G hat is still a locally compact abelian group, so it has a Haar measure. So let's call the Haar measure, you normalize it to d phi, and then the mu f, remember this mu f comes from this measure that kind of corresponds to your function f. So you integrate against this mu f of some character, you recover your function f. And turns out this function is essentially just defined by your f hat multiplied by some normalized Haar measure, okay? In other words, so if you recall how you define this mu f, so your f of x can be recovered using this d mu of f. So if you want to recover f of x, you integrate the character of evaluate at x, okay? You integrate over g hat using this mu f. And it turns out your mu f is just f hat. So what you can do is you write this nice formula. So you have the f hat of this phi d of phi. Okay, so you sometimes the Fourier inversion is stated this way. Okay, so basically your f of x can be given by a inverse Fourier transform. Okay, so this almost looks like the Fourier transform of the f hat. Okay. But it's moving backwards. Okay, you take a f hat and you integrate on the dual group, you get some function on your G. Okay, so this is called the inverse Fourier transform, and turns out in this way you can recover your function. All right, so the idea before we start, so let me just give you some idea of why we did the two technical lemma from last time and what's the main idea behind this proof. The idea is fairly simple, okay? So this kind of theorem, you already have a good candidate for your Haar measure. So if you look at this a little bit more carefully, so the idea is that you want to define this d of phi, this Haar measure is essentially this d mu f divided by f hat. So in other words, well, you know the measures corresponds to linear functional. So if you can say for every say phi inside let's say psi inside cc of g hat, and you can define a linear functional of the psi if you define it as the integral of psi times d mu f divided by f hat. Well, if you can show this I is left invariant, is strictly positive, and is linear functional, well, then this I will be a Haar measure, okay? So you can always normalize it so that this I is some Haar measure integrate against some Haar measure, all right? So the idea looks quite simple, but there is one little problem, is that your f hat can be 0, okay? So you see that if you define it this way, so this is not well defined. Why is that? Well, it's because if your psi has, let's say your psi is supported on some larger set, so that on somewhere your psi is strictly greater than 0, but your f hat is actually equal to 0, then you run into something divided by 0, which is not defined. Okay, so you can't really do that. Well, so how do we solve that? Well, the next step you realize is that, well, this choice of the f hat is actually quite arbitrary. So the Fourier transform doesn't say, well, it just works for this one particular f, okay? So it's supposed to work for all the f inside B1. In other words, this normalization doesn't really matter which f you start with. So is it possible to define a I using some different f, okay? So for some psi, you want to, well, if your support of f is, well, big enough, well, then maybe you can define it for those f, and then you try to make sense of this I, and hopefully that's going to give you a linear functional. All right, so that's kind of the idea. So let's get things started. So so with that in mind, so let's define this function I. Okay, so for every psi inside cc of g, we want to define a linear function on cc of g. So we know the support of psi is going to be compact. Let's just say is equal to k. That's compact. Okay, that's compact inside the g hat. So by the second technical lemma, I can always find some f, okay, which is positive and compactly supported, so that its Fourier transform is strictly greater than 0. So its support kind of contains the support of this psi. Okay, so by the lemma, we proved last time, there exists some f inside CC of G intersect P, so that several things happen. So first of all, the f hat is greater than or equal to 0. And if I restrict to the support of this psi, I have that something that's strictly greater than 0. Because of this property, then if I want to define an I like that, okay, so if I use the formula before, well, this is going to be well defined, okay? So I just pretend this integral is integrating over the support of psi, okay? Outside the psi, well, I just say, well, everything is 0. So now let's define my functional. So let's define this I of psi, okay? I define it as integrate psi d mu f divided by f hat, where here I require f hat satisfies these nice properties, okay? So satisfies all of these. Let's just call it maybe star, okay? So it satisfies the star. All right, so now this is well defined given a particular choice of f hat. Well, now we run into a different problem. We need to show, first of all, this I doesn't depend on the choice of f, okay? What happens if I pick two f, they give me different I, okay? Then it's not going to be good. So first of all, now let's show that I is well defined, okay? In other words, it doesn't depend on which f you pick. As long as your f satisfies star, then you get some well-defined function. All right, so this basically use the other technical lemma we need. So let's say, suppose we have two functions, f and g. They both satisfy this condition star. Well, then if you do the integral of this I of I using the first one, let's say using f, okay, so let's say integrate psi of d mu f divided by f hat. Well, what you can do is, well, because this integral is really integrate over the support of psi, and on the support, your g hat is also non-zero, strictly non-zero. So you have this is also equals to the integral. You can put a g hat on the top, and then you do d mu f, and then you need to divide the g hat. That's fine. All right, but by the lemma we showed, the g hat d mu f is you can switch the place f and g. So that's where the other technical lemma came from. So by the lemma we proved last time, this is the integral of psi f hat d mu of g, and then you divide f hat g hat. And now the f hat cancels out, so this is the integral of psi of d mu g divided by g. So this basically shows your psi, your I is indeed well defined. So this concludes that I is indeed a function defined on the entire CC of G, because every CC of G, the first lemma tells you there exists some f satisfy the star, and the other lemma tells you this I of this function using this f hat is well defined. So now you have a well defined function from CC of G to the complex. Well, now let's show that this I is indeed a linear functional and is also left translation invariance. Well, first of all, this I is clearly linear. Okay, there's nothing really need to prove. So just by observation, it's clearly linear. And suppose your psi is greater than or equal to 0, then of course, because your f hat is greater than or equal to 0, that's how I picked it. So you have that your I of this psi, which is integrate some positive things, that's going to be positive. Okay, so because your f hat is positive, your mu f is also positive by the Bachner theorem. Okay, so this is mu f also positive by the Bachner theorem, right? So you're integrating some positive function against some positive measure against something positive. Okay, so in other words, your I is going to be a positive linear functional. Okay, so remember the hard measure needs to be positive, so we have something indeed positive. Next, we want to show that this psi, this I function we define is not 0. So to do that, let's just consider what it does to some function, let's say g hat multiply by the psi. Well, by definition, this is just equals to psi divided by f hat, and then you do the g hat d mu f. And then we do the switch, we switch f and g, so you integrate psi d mu of g now, f hat and f hat cancels out. So this is the integral of psi against some mu of g. Of course, because your psi is as long as your psi is something non-zero, then some of these measures on the g hat will notice this, okay, by this integral. Okay, so this can be chosen to be non-zero for some g inside or some g hat. Okay, nice enough. Okay, so in other words, your I is going to be non-zero. Okay, so we're not getting a zero measure. All right, and we want to show is a bounded linear function. Also, let's show it is actually bounded. So let's say the support of psi is equals to k. So let's consider what happens on the support. Well, you're dividing the f hat, but your f hat is strictly greater than 0. So f hat restrict to k is strictly greater than 0. K is compact, so it's strictly bounded below. Okay, you're not dividing something that's too small. Okay, so your f hat is greater than, well, restrict to k is bounded below by some epsilon, strictly greater than 0. And then, so if you look at your integral, this psi divided by f hat d mu f, that's just going to be bounded above by this, well, if you take the absolute value, so it's going to be bounded above by epsilon times the integral of psi d mu f, and that's going to be bounded, okay? So that's bounded by some constant times norm of psi, okay? So you basically the constant is epsilon times mu f, the norm of mu f. But in any case, you have this is also bounded. So basically, we show that this I is indeed a bounded linear functional, non-zero, and is positive. Okay, so because of that, by Ree's representation, we know this I is given by some integral. Okay, so this I of psi. Now we don't need the f hat. This is going to be integral of some measure. Let's say also a positive measure. Let's say m for some. Say m greater than or equal to 0 on the g hat. Okay. All right. So now we just need to show that this m is a higher measure, and showing a higher measure is the same as showing the integral is left invariance. Okay. So that's what we left to show. So to show the left invariance, let's first observe a few things. So first of all, if I have some function, let's say g, and I conjugate on the left on some character, okay, so I conjugate phi 0. Well, then if you consider the g hat, okay, so the g hat of this phi, well, what it does is essentially just you can write the formula. So this is just g of x, and then you do the phi of x dx, phi x bar dx. And because your g, you have another copy of phi 0, so this is fx. You can think about this phi 0 multiplied by phi that character, evaluate fx conjugate. So this is essentially just the f hat evaluate at phi 0 phi, okay? So this is the left translation by this phi 0, okay? So, and another thing we may observe is that if you consider g of x, okay, so by definition, well, if g, well, f is inside B1, so g, you multiply something, some character is still inside B1. So by definition, you can recover it by the integrate against is measure mu g, okay, mu g of phi. And well, what's f of x? Well, if you look at the f of x, that's going to be equals to the integral of phi 0 phi of x d of mu g of x. Okay, so essentially this f of x is just equals to phi times g. Okay, so phi of x, phi 0 x times g. So you multiply everything by phi 0. Well, what is that? Well, because now you have a f of x is also equals to the integrate against the phi of x d mu f of x, okay? So what you can show is basically this is a change of variable formula, okay? So if you want to add something, translate something from mu f to mu g, then you pay a price of this phi 0, okay? So in other words, your d of one way of writing it, writing this one is essentially d of mu f. If I treat phi 0 phi as a single variable, I can translate it by doing integrate against mu g with just phi, okay? So that's the formula. All right, but anyways, now let's try to prove this I we defined is actually left invariant. So now let's let for every, say, psi inside CC of G, and let's just say every phi 0 inside G hat, I want to show it's left invariant. All right, so of course I need to pick something that this I function makes sense. So I might as well just pick something that has a support for the psi and also is translation by this phi 0. So let's pick some f, okay, so that the f hat is greater than 0 on the support of psi, and also the translation by this phi 0, say support of psi translate by phi 0, okay? So I don't need to change my function as I integrate and as I translate things. All right, so everything, this I function can be defined using this f hat. So let's consider what happens when you do the left translation of the psi. Well, then by definition, this is just the integral of the psi function, evaluate the phi 0 inverse times phi, and then you divide by the f hat of phi, and then d of mu f of phi, okay? And then now you want to translate this phi to you want to cancel out this phi 0 inverse, okay? So you basically do a change of variable. So what you have is that you replace the top part by psi of phi, but everything else you basically multiply a phi 0, okay? So you do the f hat of the phi 0 phi, and then you do d mu f of phi 0 phi. Well, but we proved that that's essentially just change everything into g, okay? So first of all, the d mu f of phi 0 phi, that's just equals to the d mu of g of phi, okay? So that's based on the integral. And also its Fourier transform phi f hat of phi 0 phi, that's the translation, that's also equals to the g hat of phi, okay? So in other words, this one is given also by psi of phi divided by g hat of phi, and then you do the d mu g of phi, okay? And you can show your G is also nice enough on the support side, so this I is indeed well defined. So this one, if you define this I of psi using the function G, that's what you're going to end up with, this integral, okay? So you prove that I of this last translation of psi is going to be equals to I of psi, okay? So I is indeed left invariant. So I is left invariant. And because it's left invariant, okay, so it's actually given by integral against some hard measure, okay? So in other words, I of psi has to be equals to integral of this psi function d phi for some hard measure, say hard d phi on this g hat, okay? So we can always normalize this hard measure so that this happens. All right, so now let's finish, almost finish the proof. We have one little thing. So if you consider f inside this B1, okay, so B1 of G, then you have, we basically prove that d mu f is just going to be equals to the f hat d phi. And so, well, because your mu f is now inside m of G hat, and it's written as a function times the hard measure, well, also, you know, the mu f, because when you integrate, it has to be finite. This essentially just prove the f1 hat, or f hat is also inside L1 of G hat, okay? You have to multiply L1 function, otherwise your mu f is not going to be inside M of G, not going to be bounded. All right, so this essentially finished the proof. And in conclusion, what you have is that your f of x, when you integrate, one way of doing that is because it's inside B1, is equals to integrate all the characters along your mu f, but now your mu f is essentially just given by the Fourier transform. So you integrate against the Fourier transform times some Haar measure, okay? So as just a quick corollary before we go into some examples, so if your function now is inside the L1 of G, but intersect not only inside B, but also inside P, then actually your Fourier transform is going to be greater than or equal to 0, okay? In other words, if you have something that's positive definite and L1 function, then your Fourier transform is greater than or equal to 0. So this is essentially just very quick. So by the Buckner theorem, you know that because your f is inside P, you know your mu f is greater than or equal to 0, but your mu f is equals to the f hat times the Haar measure. The Haar measure is positive, so your f hat has to be positive. Okay, so that implies f hat is non-negative.